Okay, so I thought I'd take a break from indeterminate stuff for a minute. Go back to just plain old regular staticsy type things where we don't need to use necessarily compatibility. And we're going to go back and look at torsion. And so this is from 2015 Fall Exam 3, problem number 4. I have a 1/2 inch diameter steel cable connected to a titanium tube at C. The titanium tube is fixed at support B. Calculate the normal stress, so it's normal stress, that's going to be the force in CD divided by the area of CD. The shear stress in the tube, so that's going to be the maximum torque, C, that's the outer, over J. And it's hollow, so I know this is pi over 2 C to the 4th outer minus C to the 4th inner. Okay. The vertical displacement of D, well, that's back on the cable, so that's going to have to be the delta. And when I look at this, that delta is going to come from the delta of the cable plus, as this rotates, okay, plus we're going to have to look at that phi, and we can go back and look at the circumference of a circle and realize that when we look at rotation, it's a function then of that radial length. It's that arc length that goes with our radius. And so really that phi is times r, because as we go farther out, that phi increases. So we're going to have delta of the cable, and we're going to have that rotation that we have of the tube. And then the angle of twist. So that just comes back to phi, which is torque, TL over JG. So we kind of have a mixture of axial and torsion going on. I think this is a good problem because it kind of does have all of that stuff in there. And, you know, we're going to go back and make sure that we're assuming elastic behavior. So let's look at this right here. We have a steel cable. So this is steel. Okay. And it has a length of 2 feet. So it has an original length of 24 inches. And if it's steel, E equals 29,000 KSI, and our yield stress is 36 KSI, and we have a 1/2 inch diameter, so we have pi over 4d squared, so our area is going to be pi as a number, 4 divided by diameter, 1/2 inch, 0.5 squared, 0.5 squared, and I get 0.19635 inches squared. So again, pi divided by 4 times diameter, same number. I like to run things 2, 3, 4 times, I don't know. Okay, so when I look up here at this titanium tube, I have to realize, so this is all normal stuff. This is normal stress and delta. When I look up here, I have titanium tube. That lets me know it's hollow. So if I am looking at titanium and we're looking at shear, I'm going to start with J. And J is pi over 2 C outer to the 4th minus C inner to the 4th. So I'm going to have pi over 2. Well, if the outside diameter is 5, the radius is 2.5 to the 4th minus. And if the inner is 4.475, 2 divided by, I get 2.2375. So I have a C outer of 2.5 and a C inner of 2.2375. Okay, minus 2.2375 to the 4th. Okay, so let's take that to the 4th. Make it negative, and I have a 2.5 enter to the 4th. Okay, we're going to swap those. We're going to add them because I made one negative, times pi divided by 2. So my J is 21.9886 inches to the 4th. I'm also going to need G because I'm looking at shear. So I'm going to need to know what that G is when I'm looking at the rotation. And what else am I going to need to know? I think that may be it. So G for titanium is 6400 KSI. You can look on your front sheet for that. And if the yield stress is there, we could just make sure we haven't yielded. But again, it's the shear portion. So how do we set this up? Well, the first thing I'm going to do is find the normal stress in the cable, because as I pull here, I'm going to introduce a stress. And it's going to come around, and then it's going to apply a torque in this direction, even though I've applied torque in that direction. So we have to figure out what's going on all the way up. So if I look at the normal stress in the cable, normal stress is P over A, and I can look at P as 5 kips, and area is 0.19635 inches squared. So I get 5, enter 0.19635 divided by, and I get 25.46 KSI, and I'm going to go ahead and note that that is less than yielding of 36 KSI. So my first question, okay, my normal stress in CD equals, oh, I need to go back because that whole length, that length is just up to here. So we'll deal with that in a minute. Okay, so I have normal stress, and I got a 25.46 KSI. So that's the first part of that question. Now I want to find the maximum shear stress. Well, that maximum shear stress is going to come from this torque rotating and the string pulling back. So, and we can note it's free to rotate, so it's indeterminate. And I know that this force of 5 is going to create a torque, because torque is just a fancy moment about itself, force times distance. So I have 5 kips, and I have this outer radius of 2.5 inches. So that's going to go in there. And I can note this is going to the left, and this is going to the right. So they are kind of going opposite from each other. And normally I would look at this as, okay, right hand rule, this would be my positive, that would be my negative. And then I would have to find the internal. And I would find, if I'm looking at the internal, okay, if I'm looking at the internal, twisting this way would be positive. So I know really it's a negative, it's going to be a negative shear stress and a negative rotation. But that's okay. We'll deal with that later. Okay, so I have this is going to be TC over J, so my torque is going to be 5 kips times 2.5 inches. Okay, minus 70 kip inches. So my torque is 5 enter 2.5 times 70 minus is 57.5 kip inches. Again, it's negative because of the direction, but really right now it doesn't matter that it's negative, because the material it's the same thing. We're just going to call it 57.5 kip inches. So when I want to find that stress, I have 57.5 kip inches. I have C as the outer radius, 2.5 inches. I already calculated J. So I have 21.9886 inches to the 4th. So my maximum shear stress is going to be 57.5 times 2.5 divided by 21.9886. And I get 6.54 KSI. So that's the shear stress that's in that tube. I should go back if I was giving a yield and make sure that we haven't yielded. Okay, so now when we look at angle of twist, okay, that's pretty easy. We haven't yielded, so we can use phi equals TL over JG. And I had a torque of 57.5 kip inches, and recognize it's twisting to the right, which is opposite of what the cord is doing here. And we have a length of tube out here, and the length is also going to where the cord is, which makes it super nice. So I have 5 feet times 12 inches per foot divided by J, so I have 21.9886 inches to the fourth, and then I have G, which was 6,400 KSI, and I've got kips, feet to inches, so I've got inches, so my units are working out beautifully. And when I calculate this out, I get 0.024514, and I'm going to note that the units are radians. Remember, our units are radians when we're talking about rotation because of that shear strain and that shear modulus. And anyways, so this is our rotation. As we're looking at the tube from A to B, it's free to rotate. And we're going to note that this is rotating clockwise. It is rotating that direction because that 70 is so much bigger than the 5 times 2.5. Okay, so now the next question says the angle of twist A relative. Well, we just kind of did that. So now what we need to find is the vertical displacement of D. Okay, so now we need to find vertical displacement. Okay, so what goes into that? Well, if I want to look at this, I can see that I'm kind of starting out like if we have a circle here, boink, and we go down. There's our load P, and maybe we just make like a datum. We like to have datums. We have them in dynamics. Okay, here's my original, and it's attached, and I notice that it's going to rotate. Okay, it's going to rotate clockwise, and it's going to go from here to here, which means we are coming up some sort of a delta. And when I look at that delta, I can go back and remember, we talked about this in one of our lectures about the circumference and the radial length out to the circumference and how much that position change is on the outside. And so, what was that beepy noise? Anyways, so we can find that our rotation, that delta equals phi times r. Okay, so our phi is 0.024514, and our radius is 2.5 inches out here on that edge. So that gives us the phi of, and this we're going to note is going up, okay, versus that cable stretch. The cable stretch is going to make the displacement come down, but this is how we're getting the rotational part. So if I want to look at the change of D, then it's going to be the change in length of my cable. Okay, that's going down, and then we are going to have that rotation. We're going to have that change because we have that cable. Okay, and we just need to figure out which sign convention that we want to use. So we can call, well, I drew it right here, so I said up. So we'll just say up is positive and down is negative, but it doesn't really matter. So this is positive, delta is going to be negative. So what is delta of a cable? It's PLAE, so negative. What was my force P? 5 kips. Okay. What is my length? Well, I said it was 24, and then I said we'll come back and address that. Because as I was looking this, I was like, okay, that is 24, but it also kind of goes around 1/4 of the circumference of the circle. And so our equation for a circle is it 2 pi r? Would that be the circumference is 2 pi r? And so if we are coming 1/4 of the way, it's going to be, is it 2 pi r? I may have to look up what the circumference, because my brain has just gone to mush. I apologize. It has gone to complete and utter mush. It's 2 pi r. I don't know why I question myself. So it's 2 pi r, but we are a quarter of the way around. So plus 2 pi r, but we're only going a quarter of the way around. So that is our length of rope, because it's all stretching. It just says it's attached at C, so it has this, it can still stretch, over A, and we calculated A to be 0.19635 inches squared, and E is 29,000 KSI. So we're in kips and inches, okay? And then we have plus this value. So we have plus 0.024514 times a radius of 2.5. Okay? So now I can get my calculator out, and I have 5 change signs enter, 24 enter. That goes away, that's a 2, so I have pi as a number. Okay, 2.5 times 2 divided by. We're going to add that to 24, multiply that by 5, divide by 0.19635, and divide by 29,000. Super tiny numbers. So I get delta D is negative 2.45225 times 10 to the negative 2 inches, plus, and then I have 0.024514 times 2.5 plus 0.061285 plus, and I indeed get that it is going up. It's positive. So that means this rotation right here, the rotation of that shaft, is greater than the stretch in the cable. So the end of the cable is actually moving up. Okay, so we have more of this rotating, making D go up, than what we're stretching in the cable back down. We could have had it, you know, maybe if this had been a larger force, that we would have had less rotation here and more stretch, and it could have stretched below the datum. Okay, so if this is my datum, this is where I started, there's my rotation. Well, I can also look at, this is negative because this is the delta from the force. And this is the delta from the rotation. Oh, final answer, sorry. So the final answer is the vertical displacement, delta D, is, move it over, 0.03677 inches, and it's going up.